Welcome everyone to the session. My name is Parisa Naraei, and I'm the stream owner of machine learning in healthcare here in AISC, and I'm your host today. AISC is a community of machine learning practitioners and researchers who have gathered together around the topic of AI research and engineering and products. So we are very happy that you have joined our session. And today I have the honor of having Dr. Hesam Dadafarin with us. Hesam, I'm just gonna give a little bit information on your bio and really welcoming you to the session. Thanks for accepting our invitation. So Hesam Dadafarin is the CEO of EventSend Software Development Company. At EventSend, he is leading a team of data scientists, product engineers, and designers to build custom solutions for large corporations and startup in the healthcare and medical sector. Hesam received his PhD from McGill and has more than 10 years of experience in software development and statistical modeling. In addition, Hesam has managed building complex applications for healthcare from the ground up. And he is an expert in designing ML and NLP, natural language processing platforms. So very pleased to have you on board, Hesam. Thanks for accepting our invitation one more time. You are here to talk about a very interesting paper that yourself and your colleagues published under the topic of the identifications of patients' protected health information, or as we call it, PHI, for medical free text. It's a very timely publication, I would say, and is a very important topic for us, the organizations like us, let's say in PHI as a data organizations, when we want to start methodologies.
Good afternoon, everyone. I hope all of you are safe and healthy, and thanks for listening to my talk during probably your lunchtime. As Parisa already explained, today I am going to present one of our projects, which we have done recently, and I am going to show you how you can unidentify or de-identify unstructured health data by machine learning. I believe it's well suited to this chapter because it's in the intersection of health and machine learning. So a brief overview of my presentation. Initially, I am going to introduce the main collaborators in this project. Then I will talk about the problem we saw in the industry, and after that, I will show you our journey to tackle the problem. I have been told that the audience of this talk can be general public who are enthusiastic about NLP and healthcare. So I try not to go very deep into technicality of the project and just present the overall idea. So the whole project is a three-way collaboration initiated by an organization called ICES. ICS is a not-for-profit research institute funded mainly by Government of Ontario. As most of you know, they are located in Toronto and they are connected to 6 sites at the universities across the province. They lead cutting-edge studies that evaluate healthcare delivery and outcome. In addition to ICES, we have Goran Nedadic group from the University of Manchester who have done extensive research in the identification of health data. And finally, it's us, EventSend. We are a custom software development company based in Toronto, focused on health and medical industries. We have helped small startups to large organizations such as Government of Canada to reach their critical milestones by helping them building the software. As Parisa said, we are a group of product designers, software developers, and data scientists. And we have worked on many cool projects, which I encourage you to take a look at on our website portfolio page. Great. So let's go to the main problem. As I said, ICS is one of the project collaborators, holds holds over 100 linkable Ontario production level health and non-health data sources. This includes ours around 500 data fields, which is very complex, and that translates to around 24 billion records of the data. As you can see, they have massive amount of data. These data can be refreshed daily or monthly, and sometimes quarterly and annually. Basically, whenever you go to your family doc, or God forbid you go to a hospital or do a test, A copy of your visit with the detailed results will be sent to ICS, and ICS is managed to keep and store those records for many years. So you may be curious, well, what sort of the data ICS keeps? ICS keeps both structured and unstructured data. I think most of you are familiar with structured data. These are the tabular data we often find in databases, Excel, Access, or other formats. And the thing about this structured data is that the format is defined, and they usually follow a pattern. For example, here, we know under column name, we should expect name, and last name, we should expect last name. They are a string. This is the format. On 6, we have a few items, and it couldn't vary that much. On the other hand, we have free text data. It could be physician notes, blood test results, radiographist note on MRI, and etc. In contrast to structured data, you should expect to see all kinds of information in this free text format. While most of the research is done on structured data, the one on the top, on unstructured data have invaluable amount of information, which can be used in many research. The problem with this unstructured data or free text data is that they can contain protected health information, or PHI. If you look at this example, you have patient names in it. You have dates, you have sometimes symptoms and address. And that makes it super hard to share this information with other researchers or collaborators inside the industry. There are many use cases for unstructured data. For example, they can be used to read physician notes and detect early sign of diabetes. Or imagine you want to design a clinical trial. For example, you are at Sick Kids Hospital in Toronto. It's always hard to recreate your cohort with your desired demographics. With NLP, you can read those physician notes and better screen your cohort. And finally, the same data can be used, for example, in mental health to detect bullying at the school or onset of depression. But there are legislation that reasonably limits data custodians and organizations blindly share data which might have protected health information. This legislation defines regulations to maintain security of the data and privacy of the patients or users, and also they can fine or fine those entities who don't comply with their rules and guidelines. And those fines are really high. So for example, like 2 years ago, a hospital got a fine around like $2 million because they were just careless about how they share and keep their data. Consequently, we have invaluable amount of information buried in silos and cannot be shared due to the patient privacy. So now we are talking about the problem. We have invaluable information in unstructured data, and we want to share it, but we cannot because they contain protected health information. ICS initially faced the challenge and decided to follow a few guidelines available at the time to de-identify free text data. If you look at this sentence as an example, it contains patient first and last name in addition to a date. All of those information should be de-identified before being shared with others. ICS tried to do this with 2 methods. I think it was back in 2015 or 2016. The first one is a dictionary lookup, in which you obtain a dictionary of first name, last names, occupation, etc., and check if your data has any of these dictionary items in it and de-identify them. For example, we look in this dictionary and we see that John is in our text, and then we decide to de-identify John by either deleting John or replacing with XXS, or replace John with a random name. The second approach is called regular expression. For some of the data, it's almost impractical or impossible to come up with all of these possibilities inside the dictionaries. Examples, we cannot have a dictionary of all phone numbers, email addresses, dates, and etc. So we leverage algorithm called regular expressions, which look like something like this. It's a little bit gibberish, but computer scientists understand it. What it does is that they can find patterns inside your text. For example, this guy here on the regular expression, it finds any pattern similar to this one. And it doesn't matter if it's 2020 or 2019, as far as the pattern is year, month, and date, it can detect it. Also, you can put in your regular expression different variation of the date. So instead of having year at the beginning, you can have year at the end. So with these two methods, ICS tried to de-identify the record that they had. But soon they realized that they have lots of challenges in de-identification, which I'm going to cover in the next slide. So like with the previous method that I already explained, you cannot de-identify these sentences because sometimes the information is implied within the word. For example, none of the date regular expression could catch Canada Day as a specific day. But if an attacker or someone who is curious about the patient data is looking for information, they can easily correlate Canada Day to an actual date, and then they can find the patient record. Or on the second example, Roger's CEO name can easily be Googled and matched to the patient record, although his name was not specifically found in the text. So we had John Smith, but Roger's CEO or Coca-Cola CEO or even said CEO was not in the dictionary, so we cannot find that. In more complicated scenarios, the algorithm could not differentiate between the third example, Mrs. Parkinson or Parkinson as a disease. This is very challenging too. So we have many similar cases here where a disease or a device, a medical device named after physician. And that's why it makes the dictionary lookup impractical. And it's extremely hard to catch typos, especially if it happens in names and addresses. For example, if we make a mistake in blue and young, and the typo is, for example, instead of double O, we have OU, and young is something else, then our dictionary lookup cannot find those addresses. And you can easily Google who was the naked guy who had an accident on blue and young. And probably you find the news and you get the name. The main reason it's hard to catch these issues with dictionary lookup or regular expression is that those methods ignore the context of the word. In other words, the class we are trying to assign to a word as a PHI or protected health information inside a sentence is independent of the specific word's neighbor. That's why we cannot detect Mrs. Parkinson, because a human being, when you look at this sentence, they realize that Parkinson is followed by Mrs. So this is a last name. But here, signs of Parkinson, if you look at signs, you can tell Parkinson is a disease name, not a person's name. So dictionary lookup and regular expression are incapable of detecting the neighbors. At this time, ICS started to get in touch with us and Goran's group at the University of Manchester to find a solution. To us, this is a traditional natural language processing challenge called name entity recognition. Name entity recognition is to locate and classify words inside the text into predefined categories, such as person names, organizations, location, and medical codes. And basically, it produced something like this. For example, Jim has worked at Rogers in 2006, and with NER or name entity recognition, you can have these tags or classes next to your sentences. And if you train this on medical text, then you can, in addition to person, organization, and time, you can have disease names, lab results, all those sorts of things. So in order to do name entity recognition on medical text, we started with a famous statistical model used in literature called conditional random fields. Some classifier algorithms like naive Bayes, maximum entropy, and logistic regression assume each pair of input values and labels are conditionally independent of each other, which means that if we are doing Mr. Parkinson, the label of Mr. is different than the label of Parkinson, and they are not dependent to each other. However, like in a sentence, we are dealing with a sequential data. It means that words are coming after another words, and it's a sequence. So for CRF, or conditional random fields, as you can see in this diagram and the equation, the probability of a class Y, given the word X in CRF, is dependent on the neighbors or word sequence. I don't go deep in the math, but this diagram shows that CRF, when you do labels, for example, John label is dependent on is and healthy, which makes the performance of CRFs much better than the other algorithm, traditional ones. So now we need to come up with features inside our sentence to train CRF. For example, looking at this sentence, what sort of features or characteristics can we use in our algorithm to help us define our classes better? Is it just the words itself, or we can use some other tricks? I will give you 10 seconds to think about what kind of tricks you can put in your function or algorithm as an input, which helps you to define the classes. Cool. So your time is up. I hope that you figured something. So the question is that, like, you remember dictionary lookup, we have a disease database of disease names. So we can't tell Parkinson is a disease, but we can tell Parkinson is a last name as well. But in CRF, we want to find some features between neighbors and to tell if Mrs. or is affect Parkinson class or not. So some of those features that that we are going to use in CRF, or we use in CRF, was the word itself, Parkinson itself. And then if the token is all small or all capital, for example, EEG is all capital, it has some value and it has some meaning, which helps us to define both its class and neighbor's class. What else? If the word starts with a capital letter, like Parkinson or Mrs., if the word starts with capital letter, it has some more information. Sometimes it can be a first name or last name. Sometimes it can be name of address or something. Or if it only includes alphanumeric characters, like this one, it doesn't include only alphanumeric characters, which means that it's a spatial word, a spatial token, and we should treat it differently. If it only contains letter characters, like the rest of the sentence, and shape of the word. We also, like, for each of these words in the sentence, we convert the word into a shape. And it's not just www. For example, a date, like this one, can be converted to a shape like DDDD-DD-DD, which is a digit. And we feed all of these features to our algorithm and train it. And then with the same algorithm, we can say if Parkinson is a name or is a disease.
Hesam,
Sure.
I have a question as you're presenting.
Okay.
So can I assume that these are the type of feature sets that you have implemented in your solution in MASC?
Exactly, yeah.
Okay. Thanks for confirming that.
Cool. So after testing our algorithm, we thought that we have lots of information from the past, like Ontario resident names, that we didn't leverage in our original CRF. So in our next step, we added extra feature functions to our algorithm. And this was whether any of the words in a sentence can be found in any of our dictionaries. And we add this last feature to all of the existing features. I'm going to show you the results of these two near the end of the presentation in the results section. So far, we have only tested a statistical model to help us with name entity recognition. However, there are many published literatures which have used neural networks and have promised better results in NER. So we thought that let's give them a shot. Since some of you may not be familiar with NLP, or you have performed machine learning on other data like images, in the next slides, I will show a quick brief overview of how to apply neural nets on natural language problems. In order to use neural networks on our text, we need to find a way to convert our words or tokens to vectors, which are building blocks of neural networks, as they are just matrices calculation. In image recognition, the elements of each data point could be 0 or 1 if we are talking about black and white images, or it could be simply intensity of each pixel if we are doing grayscale image, or intensity of each color channels if we are working with the color images like this one. But how can we come up with a method to convert words like Mrs. Parkinson or Mrs. to a vector, which is something like this? It's just in a list of random numbers. So one brilliant solution developed by Google engineers around 2012 was to do unsupervised learning. They call their algorithm word-to-vec, which is very famous. In unsupervised learning, we don't require tag training data. And the promise is our neural net can be trained by gathering large amount of data and let the neural net learn on its own. But how is this possible when we talk with text? We can simply gather large amount of text like books, Wikipedia, news articles, and design our network in a way to predict the next word. For example, if this is one sentence, we design a network and we just slide this window to create input and output, to create different input, and then we have an output. So in this sentence, we know that after these two, we are expecting this. After these two, we are expecting this word. And by this method, we are generating lots of training data without asking for help from any human. And then we train our network, we can easily create one hot vector for each token, multiply it by our weight matrix, and get the word vector, which is called word embedding, which can be further used to help us with our NER task. So when I say one hot vector, after we have done our pre-training with lots of tags, now if we are interested for a single word token, for example, shout, we put 0 for all of the rest of the words and make 1 only for shout, and then multiply that by our weight matrix. And the result is the word vector or representation of our word in mathematical language. We use these vectors to do NER and to de-identify our unstructured text. So the most amazing point from word-to-vec is that similar words are located together in the vector space, and arithmetic operation on word vectors can pose semantic relationships, which means that when you are looking at a sentence, usually similar words are coming next to each other, and by training your algorithm learns that proximity. So if you look at the top bar, this can be a word-to-vector representation of the word king. As explained in the previous slide, the vector is the result of doing an unsupervised training on lots of text. It's just a list of 15 numbers. We can't tell much by looking at the values. So let's color code them. We color those values around 0 white, those high values around 2 red, and those values around -2 blue. So here's our king vector with color representation. As I said, we can do arithmetic calculation on these vectors. And what I mean by that, so if you have king vector, I don't know, do you guys see my cursor or not?
No, I don't see your cursor. I'll see a beautiful presentation.
So let's see, like there was a way that I could share my, okay. Did I jump to? Oh, right. Okay, so I was saying that the first one is a king vector. You see the color represents the numbers at the top. The second one is vector representing man, and the third one is vector representing woman. Since we are working in a vector space, if you subtract man from king and added woman to it, the resulting vector would be very similar to queen, which is very amazing. Like the idea is very intuitive, but I guess it's very brilliant because you can do some semantic search for it. For example, if you are looking for Montreal basketball team, you can, and you know the name of Toronto basketball team, you can do Raptors minus Toronto plus Montreal. And then you can do search on your database and find the name of Montreal basketball team. The same for some famous classic musician. If you subtract Mercury or physics from Mercury and add classical music to it, then you probably find someone who is very famous in music.
Hesam, I have a question on this slide. So you have shown us different word vector representation. What's the typical method to find similarities and differences between multiple word embeddings?
So since vectors are just mathematical vector, you can use any mathematical function which calculates the distance between each vectors. For example, if you remember in your Math 1 or Math 2, we used to have like algebraic distance function, which calculate the difference between x and y's. But the most famous one, which is used in NLP, is called cosine, which we found it very effective.
Thanks, great.
Cool.
And as you are going to continue the presentation for the next 5 minutes, again, I want to encourage the audience to please submit your question in the chat box. And right after Hesam's presentation, I'm just going to go through that and Hesam is going to answer that. Please submit your questions. Thank you.
Okay. And Parisa, I think that I am a little bit behind. I might need more minutes, but I tried to be faster.
Okay, thanks for that. Yeah. Yes, for sure. Thanks for the reminder.
Okay, so far, we only discussed how we can convert words to vectors to be able to use them in neural networks for our name entity recognition task. Let's see what sort of neural nets we can use. The first one is convolutional neural networks, or CNNs. In CNN, we grouped our data into small independent batches. Like on your left side, this is an image, and the batch is that window of 3 by 3. And in NLP, you can use like 3 words together, and you batch them together. The main benefit of using CNN in NLP is efficiency. By grouping words into small windows and not doing the training on words or tokens one by one, we throw away some information, but we gain lots of speed. CNN can perform on much less rich embedding without mapping the entire language. This is one of the benefits. But one of the main problems with CNN is that these windows are independent from each other. So when you are in the beginning of the sentence, the cat and, the results that you get on Z0 is totally independent when you reach at the end. They got together. Which means that, like in our Parkinson example, this independency can cause problems. In order to tackle this, the second architecture comes to play, which is called recurrent neural network. It tries to address the shortcoming of CNN by which through, like in each step of learning, we feed our previous output of network additionally as an input to the existing one. For example, on your left side, if you see YT is feed again to the next step, or on the same on roll, you see that each layer's output is feed to the next step, which means that when you go through or along the sentence, each word has effect on the next word label or output. This is brilliant. It addresses the shortcoming of CNN, but it has some problem as well. So imagine that we are reading patient has fever due to flu, which is severe and has caused nausea. One of the challenge of traditional RNN is that although by the time you reach to the word flu, you know it's related to the patient. So we know flu is related to the patient because we are moving from left to right. But we don't have any information about the condition of the flu, which is severe, because we haven't reached to this step. Bidirectional recurrent neural networks have tried to address this by putting two neural networks in opposite direction next to each other and concatenate the results as an output. So now in this picture, it shows that we go not only from left to right, but also from right to left. So by the time we reach severe, we know that it has a relationship to nausea. And then when you concat these two outputs together, your neural net has more understanding and whole memory of the sentence as a whole. However, RNN is prone to a vanishing gradient, which in non-technical word, it means that although we are feeding our output to the next step, the effect gradually vanishes when we move along our sentence. So the output of patient has effect on has, and has effect on fever. But as we move along the sentence, the effect of patient diminishes, and it doesn't have any effect on nausea. So this leads to the third architecture, which I'm going to discuss today, and it's called long short-term memory, or LSTM. As I said, standard RNNs have trouble learning long-distance dependencies because of vanishing gradient problem. LSTMs try to combat this issue. In LSTM, we define a layer called memory, which is a neural net itself. The memory state helps us to remember the important information inside the sentence and forget unimportant ones. For instance, the forget gate here on your right side, the goal is to learn based on a given input how much of the cell memory you want to erase. So when you go along your sentence, forget decides if you need to forget output of patient or day. For example, in this case, day, which is just an irrelevant non-medical term, is not important for our algorithm, and forget gate can decide to forget that. There is another gate which tells us what to remember. For example, it might put more weight or more focus on patient or on Parkinson. On the second sentence, as I said, the forget gate's goal is to learn based on a given input, how much of the cell memory you want to use. When we reach the main verb to be, which is here, is diagnosed, the forget gate is responsible to tell us that to be is related to the patient, not the tremors. And hence, it should be singular, not plural. And this is how LSTM is trying to keep a memory of the whole sentence. And by keeping memory of whole sentence, it acts like a human being. So when you read the sentence, by the end of the sentence, you can tell if Parkinson was a disease or a patient name. So let's see it in action. Assume I am passing an imaginary country border, which is very sensitive to terrorism, or try to be sensitive. The officer asks me who I am, and I tell him that I am Hesam Dadafarin. And he immediately realized that Hesam is a weird noun. Is it Hassan or Hesam? Is it Arabic, Persian, or whatever? And then he looks at my passport. He says that he's Canadian, but he was born in Iran. So now he has some biases in his mind. And then the officers ask me why I'm going to their country. And I said that I am presenting at a conference to show our collaboration with ICS. But funny enough, ICS was used to pronounce as ISIS. So the moment that I put ISIS and I say ISIS, the officer gets, wow, what's going on? Now, his algorithm, his brain algorithm or her brain algorithm has a few items. Bird, I have a bird guy, Iranian background, worked with ISIS. I am working with a guy called Mahmoud, and his name is Hassan Ayatollah. And then he decides if I am allowed to go to their country or not. So depending on the neural nets inside this guy's brain, the output or decision can be varied. So So what do you think? The first one might have bidirectional STM. So she says, "Welcome to my country," because she knows that I'm not a risk to their country. But the second one uses a very simple linear equation. Y Musawi is equal to AX plus B. So he sees beer Iranian background, said you have to go to a random security check with a focus on random. So as you see, different networks behave differently, and they have more, as I said, intelligence comparing to each other.
Some very interesting example. Have
Yeah,
you faced that by any chance?
yeah. Almost every time before I got my Canadian passport. After I got that, it's usually fine.
Okay,
Yeah.
cool.
Cool. So let's look at the results, and I try to wrap it faster so we have enough time for the questions. Um, So far, I just gave you an overview of few neural net architectures and how they can be used in NLP. We have tried two methods, two bilateral neural networks with different word embeddings. The first one is Glover, which is global vector, was developed by Stanford University in 2014, I guess. And the second one is Elmo, which was developed by Allen Institute. And this is just different matrices with different methods. And they pre-trained their neural net on large text, and then they release those models for researchers like us to be able to use those vectors in our algorithm. So we trained our algorithm CRF plus dictionary, and these two neural nets, and here are the results. As you can see in the table, CRF is performing reasonably well comparing to a neural net algorithm. And the best performing algorithm was BioStems with Elmo embedding. Surprisingly, Glover didn't perform well, and our hypothesis is that embedding, which was used in Glover, was not suitable for medical data. The results are available in a paper, which I'm going to show you the link at the end of the presentation. And in addition to our core de-identification engine, we have also developed a desktop interface using Qt framework for non-technical users to be able to use our software without needing to do any coding. Also, we have developed masking modules, which help us to replace the identifiable information with random names, emails, dates, and etc. And I would like to thank all the collaborators in these projects, both from ICS and Manchester University, and my colleagues at the events. I'm not going to name them all because there are too many, but we did a very good collaboration, and I'm really proud of the results. So,
And so are we, and so are we. Hesam. Very interesting presentation. Really appreciate that you took the time and presented the solution to us. And I have a lot of questions for you. But before I start asking my question, I would start with Azadeh. She's asking you, what data set did you use to train your neural net? And were there any privacy concern around sharing ICS notes for the sake of this research project?
That's actually a very good question. There is a closed source, but it's kind of open source, but you need to accept the permission. Data source called I2B2 2014 competition. They have released around 800 physician notes, but they de-identified them manually themselves. So there are some names and last names there, but they are not related to uh, to an actual human being. And with ICS and many other organizations, like even PHI, that's always the challenge because of the regulation and privacy. No one is allowed to take those data outside of ICS. And what we did was that we actually went to ICS office to test our algorithm, and we had to work on their computers. But hopefully, with these kind of frameworks and collaboration, we provide a tool to ICS and similar organization to de-identify the data and be able to release those information to trusted researchers.
Perfect. Thanks, Hesam. Again, as I'm going through my questions, I encourage our audience to ask question. And right now I see Sina. Sina is asking you, did you think about combining the few methods you described in one engine for the holistic de-identification solution? And that was actually one of my questions as well. Thanks, Sina, for asking that.
Great. Yeah, that's actually a good question or suggestion. Usually, people call combining these guys a committee-based approach, which different algorithm vote on a token or on a class of the board, and then based on the whole consensus, we decide that if that word is a PHI or not. We haven't done it yet, but it would be super easy for us to try it and then compare it with our algorithm.
Perfect. And Hesam, just to confirm, yeah, sorry about that. Hesam, you explained that you build the desktop application for the users as well, right? That's very interesting to know because not only this is available as a Python library that we can, import and install and start training our data based on. There is also a software app that doesn't even require any coding. It's GUI based, and people can start just using it. They should just be start working with you and your company. That's all, right?
Yeah, that's a good note.
That's
Yeah.
that's a great information. So if you are an end user who doesn't need to be really bothered with the math, we still can use the solution, and that's available.
Mm.
Perfect. So my next question, Hassam, is can you give me an estimate on how much cost we are actually saving if for the health organization if we go with this approach?
Yeah, so I can give you a rough estimate. For example, if you are about to de-identify 50,000 patient records, you roughly need to spend around 5,000 hours, which is a lot, and the cost is roughly around $500,000. With our software, this is offered for free because it's open source, and you can do the whole 50,000 data points in less than 10 minutes.
Oh wow, that's impressive. Okay, thanks for speaking to that. I think that was very important information. My next question is what is the advantage of your mask framework over some other NLP based de identification solution that exists today?
Okay, so the first one is open source, so you have the liberty to bring it in house and edit it or add on top of it. Some other solution are closed source and you don't have access to the source code, and it's free, so you don't pay for it, which is very good reason. The third one is that ICS is going to train the model on its own real data and release the model under different licensing conditions. So if you do a collaboration with ICS, you probably have a chance in future to get the data or to get the model from them trained on a large, massive amount of training data and use it on your own data, which probably promises a higher accuracy comparing to the open source data.
Perfect. Okay. So I'm gonna suggest that.
Yeah.
Are there any other de identification methods available in other languages?
Um, yes, so to the best of my knowledge, there are some platforms in French, German, and also maybe Swedish. But our framework is written in a modular way, so the language can be added easily. The
Okay.
only important part is existence of pre-trained model, which nowadays, if you know the company called Hugging Face, they have released many pre-trained models in different languages, like German, French. And we have actually that feature on our roadmap to add support for other languages.
So we can include other languages. That's great to know. Yeah, and just out of curiosity, what were the main challenges working with healthcare data?
So,
Did
yeah, so I guess you are also very aware of these challenges.
Yes, we
Yeah.
are.
So the regulations are very tight, and usually for good reasons, it slows down the developers. For example, if you are a startup, you can think that, okay, I can build this, like I can predict EMR, no, not EMR, like emergency room waiting time. And I have the model, I have everything, and I go to the market and I ship it. But due to the regulation, it's not easy and it slows you down, and then you might get frustrated. The only important fact is that you need to just more time to adjust yourself to deliver the results. In some sites, you are not allowed to install even Python libraries, or you don't have access to the internet. So it takes time, but when you have the results, it's always promising.
Perfect. And one of the questions that I have on top of my mind is there are some, proprietary software, like let's say Eclipse,
Mhm.
and I know it's not, built in 2020, but how does Eclipse compare to your solution? I'm not sure even if you're familiar with that, but if you are, can you give us some insight on that?
Yeah, it came across like our research as well. So first is open source. Our solution is open source. They are closed source. So you don't really know what's going on, and you cannot fine tune your algorithm. And second, as far as I know, Eclipse is mostly for structured data. I'm not sure if you can use it for unstructured data. For structured data like name, age, date of birth, or OHIP number, uh, it is much easier to de-identify your data because you are just working with predefined format and it's not totally unknown to you. And there are existing algorithms out there which helps you to minimize the risk of exposing patient information.
Perfect. Okay, I like that.
Yeah.
Thanks for the insight. I'm just gonna check the chat box one more time to see if there are any other questions. If there is not, I can continue asking you questions. Hesam. Are you considering Microsoft and Amazon solutions? There are some competitors to your platform.
Um, they are actually, and they have promising results because they have access to lots of resources, and with a simple collaboration with a hospital or research center, um, they can reach very high accurate algorithm results. But we are not competing with them because we are making our software open source. We have already made our software open source. And what we promise is that with our solution, if you own data, you can train your algorithm the way you want it. So, but however, it's not the case for Microsoft and Amazon. And as I said before, if you are working in an organization with lots of regulation and restriction, probably those regulation doesn't allow you to use Microsoft or AWS cloud services because you are sending or uploading patients' data to cloud. Although they claim that it's super private, but your organization regulation might prohibit that. But with our solution, you can simply download it to your server or to your desktop computers, and then you can make sure that the data stay on your premises and it doesn't go outside of your premises.
Yeah. But Hesam, just to your point, maybe it might be interesting to you. We have migrated to AWS, so we are already on cloud.
Interesting.
But yeah, and that took a lot of consultation and making sure that the privacy and everything is taken care of. We actually figured out the cloud solution is even more secure than our traditional in-house servers. But I agree with everything you said. Maybe I'll consider this one as my last question. Do you ever recommend using CRF since the results were competitively close to neural net methods?
Yeah, so you're right. CR perform very well on our database, but I'm not sure if it performs well when we deal with larger data sets with
Okay.
more data variation. Like on the other hand, from engineering perspective, CRF is much faster to train, and its inference time, even on very small CPUs, is super fast. Whereas with BioLSTMs, it can take seconds to minutes depending on the board's embedding size. So if you have like smaller capacity computing capacity, and you want to have something very fast and quick, maybe you can leverage CRF. But if you have ample enough of resources, like if you are working on AWS and you can purchase like a strong server, then why not use BioSTM because it has higher accuracy.
Yeah, great. Okay, I'm just checking the chat box for the last time. I don't see any questions, but I do see that Hesam, you have provided a lot of ways for people to reach out to you. If once they think about this, they digest it, they probably can come up with some solutions. And I hope it's fine to contact you offline if there are any other questions that we have for you.
Thank you so much, and thanks to you especially for organizing this and aggregate to provide the opportunity.
Oh, thanks a lot to Hesam for joining us. That was a really interesting session for me personally. First of all, I hope it was interesting for our audience as well. And I learned a lot through this session, and I really thank you for being with us.
Thanks.
And with that said, it's the end of the session. Thanks everyone who kind of joined us in this session. The session will be recorded, and we hope that we can advertise it for the people who were unable to join our session. Thanks again, Hesam, and I hope everyone has a very nice day.
Okay, see you. Bye.